between the galaxies, between the clusters, between the filaments of matter that stretch across the known universe, there is something that should not be possible at this scale. A region of space so vast that light takes nearly 2 billion years to cross it. Inside, almost nothing. Not a dense black void sealed behind some wall of energy. Just space. Emptier than it has any right to be. Stretching further than the distance between most things you have ever been told are enormous. The biggest void we have ever found is not hiding a monster. It is not concealing a secret. It is the structure, and the fact that emptiness itself can be one of the largest features in the observable universe is among the most disturbing truths in cosmology. If this kind of deep space science grabs your attention, consider hitting like and subscribe. It helps more than you know, and we put real care into every video. Are you comfortable? Let's begin. When you look at the most famous photograph ever taken of deep space, you see abundance. The Hubble Deep Field, captured in 1995 by pointing the Hubble Space Telescope at a patch of sky so small you could block it with a grain of sand held at arm's length, revealed approximately 3,000 galaxies. Not stars, galaxies. Each one a gravitational city of 100 billion stars or more, shining from billions of light years away, packed into a sliver of sky that appeared completely empty to every telescope that came before. When the James Webb Space Telescope repeated this exercise decades later with sharper infrared eyes, it found even more. Fainter galaxies, older galaxies, galaxies so distant that their light had been traveling since the universe was barely a few 100 million years old. The images were breathtaking, and they carried a message that sank deep into the public imagination. The universe is full. Wherever you look, no matter how small the patch of sky, there is something there. Stars, galaxies, clusters, matter stretching in every direction for as far as any instrument can reach. That message is not wrong, but it is dangerously incomplete. The deep field images show you what is there. They do not show you what is missing. And what is missing is the majority of everything. To understand why, you have to step back from the photograph and look at the structure underneath it. Not individual galaxies, not clusters. The architecture of the entire observable universe, mapped across billions of light years in 3 dimensions. Astronomers began assembling this map in the late 1970s and early 1980s, using a technique that turned individual galaxy observations into something far more powerful, a census of cosmic geography. The method is called a redshift survey, and the principle behind it is elegant. Light from a galaxy that is moving away from us gets stretched as it travels through expanding space. The further away the galaxy, the more the light stretches, shifting toward the red end of the spectrum. By measuring the redshift of every galaxy in a given patch of sky, astronomers can estimate not just its position on the sky, but its distance from us. Repeat this for thousands, then tens of thousands, then millions of galaxies, and what emerges is a 3-dimensional map of how matter is distributed across the cosmos. The first generation of these maps changed everything. In 1978, Estonian astronomers Mikko Jovier and Jan Auaina-Stowe published results showing that galaxies were not scattered randomly through space. They were organized. They formed chains and clusters separated by vast, apparently empty regions. The pattern was striking, but the datasets were small and the scientific community needed more evidence before accepting that the universe had this kind of large-scale geometry. The evidence came quickly. In 1986, Astronomers Valerie de Lappa-Rahanti, Margaret Geller, and John Hucra at the Harvard-Smithsonian Center for Astrophysics completed a redshift survey that mapped a thin slice of the nearby universe. When they plotted the results, the room went quiet. The galaxies were not scattered. They were not clustered in simple blobs. They were arranged along thin walls and filaments surrounding enormous, nearly empty regions. The pattern looked like a cross-section of a sponge, or the interior of a loaf of bread, or the structure of foam. That last comparison turned out to be the most accurate. What they had found was the first clear evidence of what is now called the cosmic web, a vast three-dimensional network of matter stretching across the observable universe, organized into four basic components. Dense nodes where galaxy clusters sit at the intersections. Long, thin filaments of galaxies connecting those nodes. Flat walls and sheets forming boundaries between regions. And between all of it, occupying the spaces that the walls and filaments surround, enormous volumes of nearly nothing. Those volumes are cosmic voids. The word void is a problem. It suggests total emptiness, a perfect vacuum. That is not what a cosmic void is. A cosmic void is a region of space where the density of galaxies, of ordinary matter, and of dark matter is significantly lower than the cosmic average. Not zero, just sparse, dramatically, structurally sparse in a way that makes the void a defined feature of the cosmic web rather than a blank background. Think of it the way you would think about the interior of a foam. The material of the foam is concentrated in the thin walls of the bubbles. The bubbles themselves are mostly air. You would never describe the air inside a bubble as the absence of foam. It is part of the foam. It is what gives the foam its shape. Without the bubbles, there is no structure at all. The walls need the emptiness between them to be walls. The emptiness needs the walls to be emptiness. Cosmic voids work the same way. They are not incidental gaps left over after galaxies formed elsewhere. They are structural components of the universe's largest pattern. And they are enormous. The typical cosmic void ranges from roughly 30 million to more than 100 million light-years across. These are not exotic rarities. They are common. Surveys like the Sloan Digital Sky Survey, which mapped over 1 million galaxies across a quarter of the sky, revealed a universe stitched together by filaments and perforated by voids so large that individual galaxies are barely visible specks against the scale of the emptiness surrounding them. But the Sloan survey did not arrive in isolation. It was the culmination of a progression that took 2 decades and spanned continents. Between the first crude slices of the cosmic web drawn by Geller and Hucra in the mid-1980s, and the million galaxy catalogues of the 2000s, a series of increasingly ambitious surveys filled in the picture, each one revealing more voids, larger voids, and a cosmic web that was more structured and more empty than the previous generation of data had suggested. The 2-degree field galaxy redshift survey, conducted using the Anglo-Australian Telescope in New South Wales, was among the most important of these intermediate steps. Conducted between 1997 and 2002, it measured the redshifts of more than 220,000 galaxies across 2 broad strips of the sky, creating the first truly large 3-dimensional map of galaxy distribution at cosmological distances. Where the Center for Astrophysics survey had mapped a thin slice of the nearby universe and found 1 or 2 striking voids, the 2-degree field survey mapped enough volume to reveal the void population statistically. Voids were not isolated oddities. They were everywhere. They came in a range of sizes. They formed a connected network of underdensity threaded between the filaments and walls, and their sizes and shapes followed statistical distributions that could be compared directly to the predictions of cosmological models. This was a turning point. Before the 2-degree field survey, void science was essentially anecdotal. Individual voids were discovered, named, and studied one at a time. After it, voids became a population, a class of objects with measurable statistical properties. Astronomers could ask not just where is the nearest void, but how many voids of a given size exist per unit volume of space. They could compare the observed void size distribution to lambda CDM simulation predictions and check whether the standard model correctly predicted the emptiness of the universe in addition to its fullness. The answer was mostly yes, with important caveats. The simulations reproduced the general properties of the void population reasonably well, but the largest voids in the data, the supervoids stretching beyond 500 million light-years, appeared slightly more common and slightly emptier than the simulations expected. This tension between observation and prediction was small but persistent, and it would grow sharper as surveys grew larger and more precise in the decades that followed. The dark energy spectroscopic instrument, known as DESE, which began its main survey in 2021 from the Kitt Peak National Observatory in Arizona, pushed the measurement further still. DESE is designed to measure the redshifts of more than 30 million galaxies and quasars, plus roughly 10 million stars, across nearly a third of the sky, reaching distances of more than 10 billion light-years. Its void catalogues, still being assembled and analysed, will provide the most complete census of cosmic emptiness ever constructed, spanning a volume of the universe so large that the statistical properties of the void population can be measured with percent-level precision. The voids that Kirshner found by accident in 1981 are being mapped with the thoroughness of a geological survey, their shapes and densities recorded with the same precision once reserved for the brightest galaxies. Voids dominate the volume of the universe. Current estimates suggest that cosmic voids account for somewhere between 60 and 80% of the total volume of the observable cosmos. The matter we can see, the galaxies and clusters and superclusters that fill the photographs and populate the headlines, occupies the minority. Most people carry a picture of the universe in their minds that is upside down. They think of galaxies as the main feature and the space between them as background. The truth is the reverse. The emptiness is the main feature. The galaxies are the decoration along its edges. This realization did not arrive gently. It arrived with a specific discovery in a specific year, in a specific part of the sky, and it unsettled the astronomers who made it. In 1981, American astronomer Robert Kirshner and his colleagues were conducting a redshift survey in the direction of the constellation Boötes, a region of the northern sky visible in spring and summer from the northern hemisphere. They were cataloguing galaxy positions, measuring redshifts, and building a local map of the cosmic web. The work was methodical, routine, the kind of observation by observation data collection that underpins all of modern cosmology. Then the data revealed a hole. Not a hole in the survey, not a gap in their coverage, a hole in the universe. The team found an immense spherical region of space, approximately 330 million light-years across, in which there were almost no galaxies. The center of this region sits roughly 700 million light-years from Earth. At that distance, a volume of space this large should contain, by any reasonable estimate based on the average density of galaxies in the universe, roughly 2,000 galaxies, maybe more. Kirshner's team found almost nothing. Follow-up surveys over the next decade and a half, involving multiple teams using progressively better instruments, gradually detected a scattering of galaxies inside the region. By the late 1980s, a few dozen had been catalogued. By the late 1990s, the count stood at approximately 60. 60 galaxies where 2,000 should have been. Many of those 60 were not scattered uniformly through the volume. They were clustered along a single tube-shaped strand running through the interior, a thin residual filament of the cosmic web that somehow persisted inside the emptiness. The region became known as the Boötes Void, and for a time it was also called the Great Nothing. The numbers are stark, but they do not capture the experience of the void at a human level. For that, you need a thought experiment offered by astronomer Greg Aldering, who studied the void's interior galaxies. Aldering pointed out something that should stop anyone mid-sentence. If the Milky Way had been located at the center of the Boötes Void, instead of in our current position surrounded by the local group and the larger structures of the cosmic web, human astronomers would not have discovered that other galaxies existed until the 1960s. Sit with that for a moment. The entire history of astronomy prior to the 20th century was built on the assumption that the Milky Way was the universe. It took until the 1920s for Edwin Hubble to prove that the Andromeda Nebula was a separate galaxy, a discovery that revolutionized our understanding of the cosmos. If we had been born inside the Boötes Void, even Hubble would have seen nothing. The nearest galaxies would have been so far away and so faint that no optical telescope available before the space age could have detected them. We would have grown up believing we were alone, not alone as a species, alone as a galaxy, a single island of stars floating in a universe of perfect, uniform darkness. No neighbors, no structure, no web. That is what 330 million light-years of cosmic void does to perspective. It does not just remove galaxies from view, it removes the entire context that tells you what kind of universe you live in. The Boötes Void was a shock, but it was also a teaching moment. It forced astronomers to reckon with the fact that cosmic voids are not minor features. They are not footnotes in the margins of the cosmic web. They are major structural elements, and the largest of them can swallow the entire frame of reference that a civilization uses to understand its place in the universe. And the Boötes Void, for all its immensity, is not even close to the largest. In the years following Kirshner's discovery, as galaxy surveys grew in scope and sensitivity, astronomers began finding more voids, larger voids, voids that made the Boötes Void look like a dimple on a basketball. The second largest confirmed void, the giant void in the constellation Ka-Nis Ve Nat EC, was discovered in 1988. Its estimated diameter is between 1 billion and 1.3 billion light-years, more than 3 times the diameter of the Boötes Void. A volume of space so large that light departing from one side when the first complex multicellular life appeared on Earth would still not have reached the other side. That void contains 17 galaxy clusters, but they are concentrated in a small central region, roughly 160 million light-years across, leaving the vast outer shell of the void effectively barren. The rest is emptiness, on a scale that the word emptiness was never designed to describe. And beyond the giant void, the discoveries kept coming. In 2013, a team led by astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a study suggesting that the Milky Way itself may be sitting inside or near the center of a void. Not a small local underdensity, but a major cosmic void with a radius of approximately 1 billion light years. This structure, named the KBC Void after its discoverers, would be roughly 7 times larger than the average void, and would represent the largest cosmic void ever identified, if its full extent and depth are confirmed. The KBC Void is not a distant object. It is potentially the place you are standing right now. The air you are breathing, the ground beneath your feet, the star above you, the galaxy you live in, all of it possibly located inside a region of space where the density of matter is roughly 20% lower than the universal average. You have never noticed because you have never had a reference frame outside the void to compare against. That changes your relationship with the concept of emptiness. It is no longer something you observe at a distance. It is something you may be embedded in. But the KBC Void, as unsettling as it is to contemplate, is still debated. Its precise boundaries are hard to define. Its depth is measured through indirect methods, including the peculiar velocities of galaxy clusters in our neighborhood, and the relationship between local expansion rates and global ones. Some cosmologists accept it. Others argue that the evidence is consistent with normal cosmic variance, the expected fluctuations in matter density at large scales predicted by standard models. What is not debated is the existence of something even larger. Something confirmed. Something measured with gravitational lensing, galaxy counts, and the oldest light in the universe. In 2015, a team led by astronomer Ishtvan Sarpudi, using data from the Pan-STARRS telescope on Maui and NASA's Wide Field Infrared Survey Explorer satellite, announced the detection of an enormous supervoid in the direction of the constellation Eridanus. It was later confirmed with independent data from the Dark Energy Survey, one of the largest galaxy mapping projects ever undertaken, using the Blanco telescope in the Andes Mountains of Chile. The Eridanus Supervoid is approximately 1.8 billion light-years across. 1.8 billion light-years. The distance from one side to the other is so great that if you could somehow stand at the center and look toward the edge, the light from the nearest boundary would have left its source when life on Earth had barely begun to crawl onto land, and the void extends equally far in every other direction. It is not a bubble at the edge of our visible universe. Its center sits roughly 2 billion light-years from Earth, well within the range of our best galaxy surveys. It is real. It is confirmed. And it is the largest individual structure of its kind ever detected. Inside this supervoid, the density of matter is approximately 20 to 30% lower than the cosmic average. That sounds modest as a percentage. It is not modest when you calculate what it means in absolute terms. The volume of the Eridanus supervoid is so staggering that a 20% matter deficit across its full extent represents an amount of missing mass that exceeds entire superclusters of galaxies. The matter that should be there, according to the average density of the universe, is simply not. Not hidden. Not compressed into some smaller region. Missing from the structure. The supervoid spans roughly 1.91% of the diameter of the entire observable universe. Nearly 2% of the width of everything we can see in every direction, filled by a single underdense region. The observable universe is approximately 93 billion light-years across. The Eridanus Supervoid accounts for a slice of that expanse so large that no familiar cosmic structure provides a meaningful comparison. It dwarfs galaxies, it dwarfs galaxy clusters, it dwarfs superclusters. It is not an absence within the structure of the universe. At this scale, it is the structure of the universe, and it left a scar on the oldest light ever observed. The cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky at microwave wavelengths, carries a nearly uniform temperature of approximately 2.7 degrees above absolute zero. Nearly uniform, but not perfectly. Tiny fluctuations in that temperature, measured first by the Cosmic Background Explorer satellite, then by the Wilkinson Microwave Anisotropy Probe, and most precisely by the European Space Agency's Planck satellite, reveal the seeds of all cosmic structure. Slightly warmer spots correspond to regions that were slightly denser in the early universe. Slightly cooler spots correspond to regions that were slightly less dense. These fluctuations are measured in millionths of a degree. They are extraordinarily subtle. But one spot is not subtle. In the direction of the constellation Eridanus, the cosmic microwave background contains a region that is measurably cooler than its surroundings, spanning roughly 10 degrees across. It is called the CMB cold spot, and it has been one of the most debated anomalies in cosmology since its discovery. The supervoid aligned with it covers a far larger area of the sky, more than 30 degrees in angular diameter. The Eridanus Supervoid sits directly in front of it. The connection is physical and measurable. When photons from the cosmic microwave background, traveling for over 13 billion years, pass through a large void in the cosmic web, they experience something called the integrated Sachs-Wolfe effect. As a photon enters the void, it loses a small amount of energy climbing the gravitational potential hill created by the underdensity. As it exits the other side, it gains energy descending back toward the denser surroundings. In a static universe, the loss and gain would cancel perfectly. But the universe is expanding, and that expansion is accelerating. During the time the photon spends crossing the void has expanded further and its gravitational potential contrast has flattened. The photon gains less energy descending out than it lost climbing in. It arrives at our telescopes slightly cooler than it should be. The Eridanus Supervoid is so large and underdense that this cooling effect accounts for a measurable fraction of the cold spot's temperature deficit. The Dark Energy Survey's 2021 confirmation, using gravitational lensing mass maps constructed from background galaxy shape distortions, established the Eridanus Supervoid as the most prominent underdensity in their entire dataset and confirmed its alignment with the cold spot at a signal-to-noise ratio above 5, a void so large it has left its fingerprint on the oldest light in the universe. That sentence should land differently from anything you have heard about cosmic structures. Galaxy clusters are impressive, superclusters are vast, but they are defined by what they contain: stars, gas, dark matter, energy, structure. The Eridanus Supervoid is defined by what it does not contain, and yet it has affected the cosmic microwave background, the relic radiation from the birth of the universe itself, in a way that is measurable from Earth. Nothing at this scale is not nothing. Nothing at this scale is a feature, an actor, a force that bends the story of the universe around itself. The Boötes Void stripped a hypothetical civilization of its knowledge that other galaxies exist. The Eridanus Supervoid strips photons of their energy across a journey of 13 billion years. These are not abstract curiosities. They are demonstrations that emptiness, when it becomes large enough, stops behaving like a background and starts behaving like a structure. And what makes this even more disquieting is that the voids are not finished. They are not relics of some ancient arrangement that settled into place and froze. They are active, they are growing, they are being driven outward by the same force that is accelerating the expansion of the entire universe, and the physics of what happens inside them, in those vast, dark, nearly empty expanses where matter is sparse and gravity is weak, turns out to be unlike the physics that operates anywhere else in the cosmos. What is happening inside the biggest voids right now, and what it means for the future of the cosmic web, is where this story goes next. Finding a galaxy is straightforward in principle. It emits light. You point a telescope at the sky, the light arrives. You record it and catalogue it. The galaxy announced itself. Your job was to be paying attention. Finding a void is a fundamentally different kind of problem. A void does not emit light. It does not absorb light in any distinctive way. It does not send a signal. It does not block your view. It is defined entirely by the absence of things that would otherwise be there. Measuring a void is not like finding an object. It is like taking a census and discovering that an entire city's worth of people did not show up. You cannot photograph the missing. You can only map everyone who is present, and then stare at the gap. That distinction shapes everything about how cosmic voids are studied, how their boundaries are drawn, and why it took decades for astronomers to move from the first crude detections to the precision measurements that revealed just how structurally important these regions are. The story of void measurement is the story of learning to see nothing with increasing clarity, and the closer scientists looked, the stranger nothing turned out to be. The first generation of void detections, including the discovery of the Boötes Void in 1981, relied almost entirely on galaxy redshift surveys. Map the galaxies. Note where they cluster along filaments and walls. Note where they do not. The voids emerged as negative space, defined by the pattern of matter around them rather than by any direct observation of the void itself. This method works, but it has severe limitations. The first is completeness. A redshift survey only finds galaxies bright enough to be detected by the telescope being used. Fainter galaxies hiding in the void could be there and simply missed. Early surveys were shallow, detecting only the brightest galaxies in relatively nearby volumes of space. The voids they found could have been genuine empty regions, or they could have been populated by faint galaxies that fell below the detection threshold. The second limitation is geometry. A survey maps galaxies across a patch of sky, but the three-dimensional reconstruction depends on redshift measurements, and redshifts can be distorted by peculiar velocities. Galaxies do not sit still. They move through space under the gravitational influence of surrounding matter. A galaxy falling toward a massive cluster will have its redshift shifted by its own motion, making it appear closer or farther than it actually is. In the vicinity of a void, these peculiar velocities create a systematic distortion called the Kaiser effect, which can make a void appear elongated along the line of sight, stretched like a football rather than a sphere. Disentangling the true shape of a void from this distortion requires careful modeling. The third limitation is the most fundamental. Galaxy surveys tell you where luminous matter is. They do not directly tell you where dark matter is. And dark matter, which outweighs ordinary matter by roughly 5 to 1, is the primary scaffolding of cosmic structure. A void in the galaxy distribution could, in principle, still contain significant amounts of dark matter that simply failed to form visible galaxies. To truly measure a void, you need to map the total matter distribution, dark and luminous, together. Each of these limitations was gradually overcome as surveys grew larger, deeper, and more sophisticated. And as the measurement tools improved, voids transformed from curious blanks on galaxy maps into precisely characterized structures with measurable shapes, density profiles, velocity fields, and boundaries. The Sloan Digital Sky Survey, which began collecting data in 2000, was the first project to map the cosmic web at a scale and depth sufficient to study voids statistically rather than one at a time. Over 2 decades of observations, it catalogued the positions and redshifts of millions of galaxies across more than a quarter of the sky, reaching billions of light years into the cosmos. Void finding algorithms, software tools designed to identify underdense regions within these 3-dimensional galaxy maps, were applied to the data and produced catalogs containing thousands of individual voids. These catalogs revealed something that the early single void discoveries had only hinted at. Voids are not uniform. They are not featureless spheres of consistent emptiness. They have internal structure. This was unexpected. The intuitive picture of a void is a smooth, round, empty region bounded by walls of galaxies. The reality, as the data showed, is messier and more interesting. Voids contain tenuous wisps of structure within them. Thin filaments and faint walls thread through the interior of even large voids, subdividing them into smaller subvoids nested inside the larger one. Galaxies that do exist inside voids are not randomly scattered. They tend to sit along these internal filaments, forming a ghostly skeleton of structure that mirrors the cosmic web outside, but at much lower density. Researchers studying these void interiors found that the internal structure follows the same hierarchical pattern that governs the cosmic web at all scales. Just as the universe is organized into a web of filaments surrounding voids, the interior of a large void is organized into a finer web of fainter filaments surrounding smaller voids. It is structure within structure, emptiness nested inside emptiness. The pattern recurs at smaller scales like a fractal, though it eventually fades below the threshold where individual galaxies can trace it. A survey of 60 void galaxies selected from the Sloan data, led by astronomer Catherine K. Reckel, confirmed that many of these interior galaxies are not isolated. Some exist in small groups. Some are interacting with neighbors along the faint filaments. One system, catalogued as VGS-31, turned out to be a trio of galaxies aligned along a hydrogen filament deep inside a void, a miniature version of the large-scale interactions that happen in the dense parts of the cosmic web. The void was not dead. It was sparse. It was quiet. But it was not structurally featureless. This discovery carried a subtle but important implication. A void is not the absence of structure. It is structure at a different density, following the same gravitational rules as the rest of the universe, but operating in a regime where matter is so thinly spread that the results look qualitatively different. A desert is not the absence of geography. It still has dry riverbeds, dunes, and basins carved by the same forces that sculpt mountains elsewhere. It is simply a landscape where less material was available, and the features that formed are correspondingly sparse and fragile. Voids are the cosmic equivalent. The same gravitational physics, the same dark matter dynamics, just less of everything, producing a whisper of structure where the rest of the universe produces a roar. The discovery of void substructure also made the measurement problem harder. If the interior of a void is not uniform, then defining where a void begins and ends requires a decision about what density threshold counts as the boundary. Different void finding algorithms use different definitions, which means different catalogs can disagree about the number, size, and shape of voids in the same survey data. Some algorithms define voids as spherical regions below a fixed density threshold. Others use Voronoi tessellation, dividing space into cells around each galaxy and identifying large cells as void candidates. Others grow voids outward from local density minima until they reach a specified density wall. These methodological differences are not a flaw in the science. They reflect the genuine ambiguity of defining a boundary for something that has no sharp edge. A void does not end at a wall the way a room ends at a doorframe. It transitions gradually from lower density to higher density, with the boundary sitting somewhere along a smooth gradient. Where you draw the line determines what you measure. This is the price of studying a structure defined by absence. There is no bright edge to anchor your ruler against. Despite these challenges, the convergence across different methods and different surveys is striking. Voids are real. Their general properties are robust. And when astronomers moved beyond galaxy positions and began using entirely independent methods to probe void structure, the picture held together. The most powerful of these independent methods is gravitational lensing. Every concentration of mass, whether visible or dark, bends the path of light passing near it. This is a prediction of general relativity, confirmed observationally since the early 20th century. When light from a distant background galaxy passes through a region of the cosmic web, its path is deflected by the total matter along the line of sight, including dark matter that emits no light of its own. The result is a subtle distortion of the background galaxy's shape, a slight stretching in a preferred direction that encodes information about the total mass distribution between the source and the observer. By measuring these tiny shape distortions across millions of background galaxies, astronomers can reconstruct a map of the total matter distribution, dark matter included, without relying on the positions of foreground galaxies at all. This technique, called weak gravitational lensing, is the closest thing cosmology has to an X-ray of the cosmic web. It reveals the skeleton, not just the skin. When lensing mass maps were constructed in the direction of the Eridanus Supervoid, the results went further than anything galaxy surveys alone could show. The Dark Energy Survey's Year 3 analysis combined its red magic catalogue of luminous red galaxies with lensing shape measurements to probe not just where visible galaxies were missing, but where the total gravitational mass was depleted. The lensing signal revealed a region where the full matter content, dark matter included, fell significantly below the cosmic average. The void was not an artifact of missing faint galaxies. It was a genuine deficit of everything. The power of this technique deserves a moment of emphasis, because what gravitational lensing does for void science is something no galaxy survey, no matter how large, can accomplish alone. A galaxy survey tells you where visible matter is. It counts the galaxies. It records their positions and brightnesses. But it cannot tell you what is happening in the spaces between the galaxies. It cannot tell you whether a region that lacks visible galaxies also lacks the invisible dark matter scaffolding that galaxies would normally form around, or whether the dark matter is there and simply failed to produce anything luminous. Gravitational lensing answers that question directly. It measures the total gravitational field along the line of sight, produced by every type of matter, visible and invisible, without requiring that matter to emit or absorb any light. Every photon from a background galaxy carries information about every gravitational field it passed through on its journey. By measuring the tiny, coherent shape distortions across millions of these background galaxies, astronomers reconstruct the total mass distribution in the foreground, including inside voids. When this technique was applied to the Eridanus Supervoid and confirmed a genuine deficit in total mass, not just galaxy counts, it closed a loophole that had lingered since the earliest void discoveries. For decades, it had been theoretically possible that voids were populated by dark matter halos that simply never formed visible galaxies. Perhaps the physics of gas cooling, star formation, or some other baryonic process had failed inside voids, leaving dark matter structures intact but invisible. The lensing maps ruled this out. The dark matter itself was depleted. The gravitational scaffolding that galaxies normally form around was missing. The void was not a region where galaxy formation failed. It was a region where the raw materials for galaxy formation were not there. This distinction matters enormously for the interpretation of what a void is. A void where galaxy formation failed is a place where the same basic infrastructure exists, but something went wrong with the surface layer. A void where the dark matter itself is depleted is a place where the infrastructure was never built. The second kind of void is far more fundamental, far more structurally significant, and far more consistent with the picture of voids as features sculpted by physics from the earliest moments of cosmic history. The lensing analysis also revealed an interesting tension. The amplitude of the lensing signal from the Eridanus Supervoid at the center of the cold spot was approximately 30% lower than what standard cosmological simulations predicted for a void of comparable size and density contrast. This means the void is either slightly different from what the standard lambda CDM model expects, or the model's predictions for void lensing profiles need refinement. Either way, the measurement pushed the Eridanus Supervoid from a curiosity into a genuine test case for cosmological models. Gravitational lensing confirmed that the void is real in the total matter distribution. But another class of measurement revealed something arguably more disturbing. The void is not just sitting there, it is moving the universe around it. Galaxies near a void do not simply occupy space passively. They feel the gravitational imbalance created by the underdensity. Matter outside the void, in the denser filaments and walls, exerts a stronger gravitational pull than the sparse interior. The result is that galaxies inside and near the edges of a void experience a net outward flow, drifting away from the void's center and toward the surrounding structures. These are called peculiar velocities, and they are distinct from the general expansion of the universe. They are motions caused by local gravitational imbalances layered on top of the cosmic expansion. Measuring peculiar velocities is technically demanding. You need to know both the galaxy's redshift, which includes both the cosmic expansion and the peculiar velocity, and an independent estimate of its distance. So you can subtract the expansion component and isolate the motion caused by local gravity. Several methods exist for independent distance measurement. including the use of Type 1a supernova as standard candles and the Tully-Fisher relation, which connects a spiral galaxy's rotation speed to its intrinsic brightness. None of these is easy. All carry significant uncertainties, but when applied across large samples of galaxies near known voids, the peculiar velocity field reveals the gravitational footprint of the void. The flow pattern is distinctive. Galaxies stream outward from the void center, accelerating as they approach the dense walls. The velocity field traces the shape of an invisible basin in the gravitational landscape. Like watching currents in a river reveal the contour of the riverbed beneath the surface. You cannot see the basin directly, but you can see everything moving in response to it, and from the motion, you can reconstruct what must be there, or rather, what must not be there. This technique became critical in the study of the KBC Void, the enormous underdensity that may surround our own Milky Way. Because we are inside the KBC Void, or near its center, we cannot step outside and photograph it the way we can photograph the Boötes Void or the Eridanus Supervoid from a distance. We have to infer its existence from the behavior of everything around us. The original identification of the KBC Void by Keenan, Barger, and Cowie in 2013 relied on galaxy number counts. They measured the density of galaxies in our local cosmic neighborhood and compared it to the expected density at greater distances. The result was a significant local deficit. A region extending roughly 1 billion light-years in radius, where galaxy counts were measurably below the cosmic average. The underdensity was real, and its scale was enormous. But galaxy counts alone could not prove that the underdensity was gravitationally significant. Maybe we just happen to live in a region with fewer bright galaxies, while the total matter, including dark matter, is close to average. To test that, astronomers needed independent evidence. One line of evidence came from the kinematic Sunyaev-Zeldovich effect, a subtle distortion of the cosmic microwave background caused by the motion of galaxy clusters through space. When a massive galaxy cluster moves relative to the cosmic microwave background, its hot gas scatters microwave photons in a way that creates a tiny temperature shift in the direction of the cluster's motion. By measuring these shifts across many clusters, astronomers can determine how fast the clusters are moving and in what direction. In 2017, University of Wisconsin student Ben Hoshit analyzed the kinematic Sunyaev-Zeldovich signals from galaxy clusters within and near the proposed KBC Void. The cluster motions were consistent with what would be expected if the void were real, with clusters flowing outward as predicted by the gravitational influence of a large underdensity. The result did not prove the KBC Void beyond all doubt, but it added a second, independent line of evidence supporting its existence. The third and most recent line of evidence arrived in 2025, when physicist Indranil Bahnik and colleague Vasileios Karlaitziadis published an analysis using baryon acoustic oscillations, a completely different cosmological probe. Baryon acoustic oscillations are among the most elegant tools in cosmology. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma in which matter and radiation were tightly coupled. Sound waves, literal pressure waves, propagated through this plasma at roughly half the speed of light. When the universe cooled enough for neutral atoms to form, the plasma released its grip on the photons, and the sound waves froze in place. The pattern they left behind is imprinted in both the cosmic microwave background and the distribution of galaxies, appearing as a slight statistical excess of galaxy pairs separated by a characteristic distance of roughly 500 million light years in today's expanded universe. This characteristic distance acts as a cosmic ruler. Because astronomers know the physical size of the baryon acoustic oscillation scale from the physics of the early universe, they can compare the apparent angular size of this ruler at different distances to measure how the universe has expanded over time. It is one of the most precise probes of cosmic expansion available. BAH-Nick and Carlitzidis realized that if the Milky Way sits inside a large void, the void's gravitational influence would slightly distort the baryon acoustic oscillation signal in nearby galaxy surveys. The outward flow of matter caused by the void would add an extra velocity component to the redshifts of galaxies within and near the void, making the expansion rate appear locally higher than the global average. This would create a subtle but measurable distortion in the baryon acoustic oscillation angular scale at low redshifts. Their analysis of 20 years of baryon acoustic oscillation measurements found that the data were consistent with the local void. The baryon acoustic oscillation signal at low redshifts showed a slight deviation from what the standard lambda CDM model predicts for a perfectly homogeneous universe, and the deviation matched the pattern expected from a void with properties similar to the KBC Void. This result is significant for a reason that extends far beyond void science. It connects directly to one of the most urgent, unresolved problems in modern cosmology. For over a decade, astronomers have been grappling with a discrepancy called the Hubble tension. When the expansion rate of the universe is measured using local distance indicators, such as Cepheid variable stars and Type 1a supernovae, the result is consistently higher than when the expansion rate is inferred from the cosmic microwave background using the standard lambda CDM model. The local measurement gives a value of approximately 73 kilometers per second per megaparsec. The cosmic microwave background prediction gives approximately 67.4. The gap between these two numbers has persisted and even strengthened as both measurement techniques have improved. Dozens of proposed explanations have been offered. New physics beyond the standard model, systematic errors in distance measurements, modifications to dark energy. None has achieved consensus. The KBC Void offers a different kind of explanation. If we are inside a large underdensity, the outward flow of matter from the void adds an extra component to the apparent recession velocities of nearby galaxies. When astronomers measure the local expansion rate, they are measuring the cosmic expansion plus the void-induced outflow. The result is a local Hubble constant that appears higher than the true global value. The weight of the Hubble tension as a scientific problem cannot be overstated. This is not a minor discrepancy buried in a technical journal. It is a disagreement between two of the most carefully calibrated measurement chains in the history of physics, each refined over decades by independent teams using fundamentally different methods, each producing results that have become more precise and more incompatible with the passage of time. On one side is the distance ladder, the painstaking chain of measurements that starts with parallax distances to nearby stars, steps outward through Cepheid variable stars in more distant galaxies, and reaches cosmological distances through Type 1a supernovae, standardizable explosions whose intrinsic brightness allows astronomers to determine how far away they are. The distance ladder gives a Hubble constant of approximately 73 kilometers per second per megaparsec. On the other side is the cosmic microwave background, the afterglow of the Big Bang itself, measured with extraordinary precision by the Planck satellite, and analysed using the standard lambda CDM model of cosmology. When the physics of the early universe is used to predict what today's expansion rate should be, the answer is approximately 67.4 kilometers per second per megaparsec. The gap between 73 and 67.4 has persisted through every attempt at resolution. Systematic errors in the distance ladder have been hunted with obsessive care. Calibration techniques have been cross-checked and refined. Alternative distance indicators have been tested. The measurements have not converged. They have, if anything, drifted further apart as precision has improved. The tension now exceeds 5 sigma in some analyses, a threshold that in particle physics would be considered a discovery. In cosmology, it is treated as a crisis. Hundreds of papers have proposed solutions. Some invoke new particles that altered the expansion rate in the early universe. Some modify the behavior of dark energy, allowing it to change over time. Some propose entirely new physics beyond the standard model. None has achieved consensus. The problem has consumed a significant fraction of the theoretical cosmology community's attention for over a decade, and the absence of a clean resolution has led some researchers to suspect that the answer may not lie in exotic new physics at all, but in something closer to home. Nick calculated in previous work that the KBC Void could produce a local Hubble constant approximately 11% higher than the global average. That is remarkably close to the observed discrepancy. The void does not need to be invoked as a speculative fix. It is a measured structure whose gravitational effects can be calculated from known physics. If its full extent and depth are confirmed, it may resolve the Hubble tension without requiring any modification to the laws of physics. This is an extraordinary possibility. One of the most debated problems in all of cosmology, a disagreement that has consumed thousands of research hours and generated hundreds of papers, might be caused not by exotic new physics, but by the fact that we happen to be sitting inside one of the universe's largest empty regions. The void is not just a feature of the map, it is distorting the map. And we did not notice because we had no vantage point outside it from which to see the distortion. Not every cosmologist is convinced. The lambda CDM model predicts that the universe should be approximately homogeneous on scales larger than a few 100 million light years. A void as large as the KBC Void, with a radius of roughly 1 billion light years and a density contrast of 20%, is extremely unlikely in standard simulations. Some estimates place it as a 1 in a billion event in the lambda CDM framework. If the KBC Void is real and as deep as the data suggest, it may not just resolve the Hubble tension. It may challenge the standard cosmological model itself. This tension between the void's measured properties and the model's predictions is part of an ongoing and active scientific debate. The evidence in favor of the void is growing. The baryon acoustic oscillation results from 2025 add a new and independent line of support. Galaxy count surveys, peculiar velocity measurements, and kinematic Sunyaev-Zeldovich analyses all point in the same direction. But the theoretical discomfort with a void this large within the standard model means that the question is not yet settled. What is settled is that voids have moved from the margins of cosmology to its center. They are no longer curiosities found by accident during galaxy surveys. They are precision tools, laboratories for testing fundamental physics, and potential keys to resolving the deepest disagreements in the field. The measurement revolution that made this possible unfolded over 4 decades. From Kirshner's first startled look at a blank patch in his galaxy map, to the sophisticated lensing mass maps and baryon acoustic oscillation analyses of the 2020s, each generation of instruments and techniques peeled back another layer of what voids are and what they do. And every layer revealed the same unsettling truth. The more precisely you measure a void, the more structurally important it becomes. The void is not a mistake in the cosmic web. It is not a failure of galaxy formation. It is not a gap waiting to be filled. It is a region where the universe is operating under different rules, where the balance of forces is tilted away from gravity and toward expansion, where the physics of structure formation produces outcomes that are qualitatively different from what happens in the dense filaments and clusters. The voids are not empty in the way a room is empty when the furniture is removed. They are empty in the way a low-pressure zone is empty in the atmosphere. The low pressure does not just sit there passively. It drives the weather. It pulls air from surrounding regions. It shapes the circulation of the entire system. Cosmic voids do the same thing at a scale that encompasses billions of light years. And the force that drives them, the energy that dominates inside them and pushes their walls ever outward, is the most abundant and least understood component of the universe. But the measurements revealed something beyond the void shape and position. Inside the emptiest regions of the cosmic web, the balance of forces is not what most people assume. Gravity, the force that built every galaxy and cluster, does not rule everywhere equally. In the deep interior of a cosmic void, something else takes over. Something that has been operating quietly for billions of years, reshaping the voids from within, pushing their boundaries steadily outward, and slowly, persistently changing the architecture of the universe in ways that the dense, luminous structures we celebrate in photographs cannot resist. Understanding that force, and what it does when left unopposed inside the deepest voids, is where this story turns next. Because the voids are not standing still right now. They are changing, and the change has consequences that reach far beyond the boundaries of any single empty region. The instruments that reveal this picture are already being surpassed by a new generation. NASA's Nancy Grace Roman Space Telescope, now operational, is surveying the sky with a field of view 100 times larger than the James Webb Space Telescope, mapping the cosmic web across billions of light years with the precision needed to measure individual void density profiles and growth rates. The European Space Agency's Euclid mission is conducting the most ambitious survey of cosmic structure ever attempted, covering 15,000 square degrees of sky and measuring the shapes and redshift of billions of galaxies to trace the dark matter web and the voids within it. The Vera C. Rubin Observatory, with its unprecedented survey speed, will build the most detailed three-dimensional map of the nearby universe ever assembled. These instruments will not merely find more voids. They will measure how voids evolve over cosmic time, how their density profiles change as dark energy drives their expansion, and how the void population constrains the fundamental parameters of the universe, including the equation of state of dark energy, the total mass of neutrinos, and the validity of general relativity on the larger scales. Cosmic voids have become, in the words of one research team, the regions where cosmic expansion is most clearly expressed. They are where dark energy shows its hand. They are where the future of the universe is being written in real time, not in the blazing furnaces of stars or the violent collisions of galaxy clusters, but in the quiet, expanding, darkening spaces between them. And the full weight of what that means for the structure of the universe and for the picture of reality that lives inside the human mind has not yet been confronted. That confrontation is next. There is a mistake that most people make when they first hear about cosmic voids, and it is so natural, so instinctive, that correcting it requires a deliberate act of imagination. The mistake is to think of a void as leftover space, as the part of the universe that was passed over when galaxies formed, the way a puddle forms around rocks and leaves behind a dry patch. In this picture, the void is incidental. It is what remains when gravity has finished pulling matter into filaments and clusters and walls. The void is a byproduct, not a product. Background, not foreground. This is wrong. And understanding why it is wrong is the key to grasping what makes the biggest voids in the universe so structurally significant, so scientifically powerful, and so deeply unsettling. Cosmic voids are not the leftover space that gravity forgot. They are regions that gravity actively shaped. Through a process that began less than a billionth of a second after the Big Bang and has continued without interruption for over 13 billion years. The process starts in the earliest moments of the universe, in the hot, dense plasma that filled the cosmos during its first few 100,000 years. Yeah, the distribution of matter was nearly uniform, but not perfectly so. Tiny quantum fluctuations, variations in density so small they amounted to differences of roughly 1 part in 100,000, were imprinted across the primordial medium. These fluctuations were random. Some regions were slightly denser than average, others were slightly less dense. At the moment of their creation, the difference between a future galaxy cluster and a future void was negligible, a whisper of variation against a roar of uniformity. But gravity amplifies whispers. In a region that was slightly denser than average, gravity pulled surrounding matter inward. The region grew denser. As it grew denser, its gravitational pull strengthened. More matter fell in. The process accelerated. Over hundreds of millions of years, these overdense seeds collapsed into the filaments, walls, and clusters of the cosmic web. Stars formed. Galaxies assembled. The bright, visible structures of the universe came into existence through a cascade of gravitational amplification that turned tiny initial imbalances into the trillion-star architectures we observe today. In a region that was slightly less dense than average, the opposite occurred. The surrounding overdense regions pulled matter outward, away from the underdense center. As matter flowed out, the region became emptier. As it became emptier, its gravitational pull weakened further, which made it even less able to compete for matter against the denser regions around it. The void deepened, not because something scooped matter out of it, but because the gravitational competition was rigged from the beginning. An underdense region loses matter to its neighbors in the same way that a shallow well loses water to a deeper one. The physics is the same. The result is opposite. Where overdense regions collapse and build, underdense regions expand and empty. This is the first critical insight. Voids did not form passively. They formed through an active process, the gravitational evacuation of matter from regions born with a slight initial deficit. The seeds of every void in the cosmic web were planted in the quantum fluctuations of the first fraction of a second of cosmic history. The voids you see in galaxy surveys, stretching tens or hundreds of millions of light years across, are the grown descendants of those primordial seeds, amplified across 13 billion years of gravitational evolution. Research into the formation of large multi-scale voids has shown that the process depends critically on the interaction of density perturbations at different scales. Small-scale perturbations alone produce halos and short filaments everywhere, but do not generate the vast empty regions that characterize the real cosmic web. Large-scale perturbations must be present and must synchronize with medium-scale perturbations in their underdense phases to create the conditions for void formation. When these perturbations align in their negative phases, they suppress the growth of small halos inside the underdense region, preventing galaxies from forming even where the local conditions might otherwise permit it. The void is not simply a region where galaxies fail to appear. It is a region where the combined action of perturbations at multiple scales actively prevented their formation. The timescale over which this process operates is itself part of what makes it so disquieting. The quantum fluctuations that seeded the voids were generated during inflation, in the first unimaginably tiny fraction of a second after the Big Bang, a period so brief that no human unit of time can meaningfully describe it. Those fluctuations were imprinted as variations of roughly 1 part in 100,000. Differences so slight that if you map them onto the temperature of a room, the warm spots and cold spots would differ by less than 1,000th of a degree. And then gravity went to work. For millions of years, the variations were too small to produce visible effects. The universe expanded. Matter cooled. The plasma released its photons and became transparent. And still the fluctuations were subtle, barely detectable, indistinguishable from uniformity to any instrument that was not specifically designed to find them. But the process was cumulative and self-reinforcing. Every year, every million years, every 100 million years, the slightly underdense regions grew slightly emptier, and the slightly overdense regions grew slightly denser. The asymmetry between them deepened with the patience of geology multiplied by 1,000. By the time the first galaxies began to form, roughly 200 to 400 million years after the Big Bang, the void regions were already distinguishable as large underdensities in the matter distribution. By the time the universe was 1 billion years old, the first recognizable voids had taken shape, bounded by the first recognizable filaments. And the process did not stop. It continued through the entire age of the cosmos. 13.8 billion years of unbroken gravitational evacuation. Each epoch deepening the voids further, each era making the contrast between the dense and the empty more pronounced. The Eridanus Supervoid at 1.8 billion light-years across is not a structure that appeared suddenly. It is the product of nearly 14 billion years of matter slowly, steadily, gravitationally withdrawing from a region that was born with a fractional deficit so small it would be invisible to any instrument that exists today if it were measured at the moment of origin. The patience of the physics is what makes the scale possible. No catastrophe carved the void. No explosion cleared the matter away. No force acted violently. The void grew through a process as gradual as the wearing of stone by water, except that it operated across billions of years and produced a feature spanning almost 2% of the diameter of the observable universe. The universe built one of its largest structures through the quietest, slowest, most persistent mechanism available to it. the differential pull of gravity acting across time. This makes voids deeply sensitive to the initial conditions of the universe. The size distribution of voids, the depth of their density profiles, and the way they cluster relative to each other all depend on the spectrum of primordial fluctuations generated during inflation, the hypothesized period of exponential expansion in the universe's first moments. Voids carry information about the birth of the universe in their shapes. They are fossils of the quantum fluctuations that seeded all of cosmic structure, and they preserve that information more cleanly than the overdense regions. Because the physics inside voids is simpler, that last point deserves emphasis. In the dense parts of the cosmic web, structure formation is non-linear. Matter collides, merges, shocks, heats, cools, fragments, and collapses in ways that are computationally expensive to model and difficult to predict analytically. The information about initial conditions gets scrambled by the violence of gravitational collapse. Inside a void, the physics remains much closer to linear. The density contrast evolves smoothly. The velocity field is orderly. The growth of structure is gentle rather than catastrophic. This means that the signatures of the primordial fluctuations are better preserved inside voids than anywhere else in the universe. Cosmologists recognized this and began treating voids not just as features of the cosmic web, but as laboratories for fundamental physics. The density profiles, velocity fields, and abundant statistics of voids encode information about some of the most important open questions in physics. The equation of state of dark energy, the total mass of neutrinos, the validity of general relativity on the larger scales, the growth rate of cosmic structure over time. Each of these can be probed by measuring how voids behave, how they grow, how they are distributed, and how they distort the light and radiation passing through them. And at the center of this program is the fact that drives the entire story of cosmic voids into territory that most people have never considered. Inside every void, the balance of forces is different from anywhere else in the universe. In the dense filaments and clusters of the cosmic web, matter's gravity dominates. The gravitational attraction between galaxies, gas, and dark matter holds structures together, resists the expansion of space, and drives the ongoing process of structure formation. Dark energy, the repulsive force that accelerates cosmic expansion, is present everywhere. But in these dense regions, it is outgunned by gravity. The structures hold. Galaxies remain bound to their clusters. Filaments persist. Inside a void, the balance tips. There is so little matter that gravity's hold weakens to a whisper. Dark energy, which operates as a property of space itself and does not depend on the presence of matter, continues at full strength. The result is a region where the dominant force is not the attractive pull of gravity, but the repulsive push of dark energy. Think of an orchestra performing a symphony. In the dense parts of the cosmic web, every instrument is playing. Brass, strings, woodwinds, percussion, all filling the hall with sound. The quietest instrument in the ensemble, a single triangle, is there, tapping out its rhythm, but you would never hear it above the rest. Now, imagine the rest of the orchestra leaving the stage, one section at a time. The brass falls silent. The strings stop. The woodwinds fold their music stands. Eventually the triangle is the only instrument left. And in the silence of the empty hall, that single quiet tap becomes the loudest sound in the room. That is what dark energy does inside a cosmic void. It is the same everywhere. But in the emptiness, it is the only force still operating at full strength. And its effect, which is to push space apart, to accelerate expansion, to drive matter further from the void's center, becomes the dominant process shaping the void's evolution. This is why voids grow. Over cosmic time, the expansion of space inside voids proceeds faster than in the surrounding dense regions. The walls and filaments that bound the void are gravitationally bound structures, held together by the mass they contain. But the void interior, where dark energy dominates, expands more rapidly. The boundary between the void and the wall is not a rigid barrier. It is a gradient, a transition zone where the expansion rate shifts from the void's faster rate to the wall's slower rate. And as the void expands, that transition zone moves outward, encroaching on the surrounding structure. This is not erosion in the familiar sense, where material is worn away and carried downstream. It is something stranger. The banks of the void do not collapse inward. The void pushes them outward. The river grows wider not because the banks are weak, but because the space between them is actively expanding. The process is slow by human standards, but relentless on cosmic timescales. Over billions of years, voids grow larger, their interiors become emptier, and the filaments and walls between them become thinner and more tenuous. And when two neighboring voids grow large enough, their boundaries overlap. The thin wall separating them erodes. The voids merge into a single, larger supervoid. This process has been happening throughout cosmic history. The largest voids we observe today, including the Eridanus Supervoid, are likely the products of multiple mergers, smaller voids that grew and combined over billions of years to produce structures spanning more than 1 billion light years. The implication is stark. The cosmic web is not a permanent architecture. It is a temporary arrangement, a snapshot of an ongoing process in which the voids are slowly winning. Given enough time, the expansion driven by dark energy inside the voids will thin the filaments until they can no longer sustain their structure. Galaxy clusters, gravitationally bound and resistant to the expansion, will persist as isolated islands, but the filaments connecting them will fade. The walls will dissolve. The cosmic web will unravel, leaving behind a universe of isolated clusters surrounded by ever-expanding emptiness. The mechanics of this unraveling are worth following through, because they reveal something about how the universe ages that is not captured by the more familiar story of stellar evolution and galactic mergers. Begin with a filament. A cosmic filament is a thread of galaxies, gas, and dark matter connecting two galaxy clusters across tens or hundreds of millions of light years. It is not a rigid structure. It is held together by the gravitational attraction of the matter it contains, but it is also subject to the expansion of space along its length. In the present-day universe, gravity wins. The filament persists. Galaxies within it drift slowly toward the denser nodes at either end, feeding the clusters while maintaining the filament's overall structure. But as the voids on either side of the filament continue to expand, the filament is placed under increasing stress. The expansion is not applying force in the mechanical sense, not pulling the filament apart the way you would stretch a rubber band. Instead, the space within and around the filament is expanding, and the expansion rate inside the flanking voids is higher than the expansion rate within the filament itself, because the voids are dark energy dominated while the filament is matter dominated. Over time, this differential expansion effectively widens the gap between the filament and the void centers, stretching the filament's environment even as the filament's internal gravity tries to hold it together. There is a threshold. When the density of a filament drops below a critical value, its self-gravity can no longer resist the surrounding expansion. The filament does not snap, it thins, its galaxies drift apart, its gas disperses, the dark matter halo that gave it structure dilutes to the point where it is no longer gravitationally distinct from the void around it. The filament fades into the void, not through destruction, but through dilution. When a filament fades, the two clusters it once connected lose their bridge. They become gravitationally isolated from each other. No matter will flow between them. No gravitational interaction will connect them. They will continue to exist as bound structures, their internal dynamics unchanged, but their relationship to each other and to the larger cosmic web will be severed. Each cluster becomes an island. This process does not happen to all filaments simultaneously. The thinnest and least dense filaments will fade first. The most massive, connecting the richest clusters, will persist longest. But the direction is universal and the endpoint is the same. Every filament is subject to the same differential expansion. Every filament exists in a universe where the voids flanking it are growing faster than the filament can replenish itself. The question is not whether a given filament will dissolve, but when. The cosmic web is aging. Not in the way that a star ages, burning through fuel on a predictable timeline. In a quieter way. The web is thinning. Its threads are losing definition. Its voids are gaining volume. The architecture that organizes the distribution of matter across the observable universe is being gradually and irreversibly simplified, from a complex, interconnected network of filaments and walls and clusters and voids, into a scattering of isolated gravitational islands, adrift in a featureless expansion. That future is unimaginably distant. Hundreds of billions of years from now, long after the last stars have burned out and the universe has entered what cosmologists call the dark era. But the process is already underway. Every void in the cosmic web is growing right now. Every filament is being stretched. The architecture of the universe is being slowly dismantled by the very emptiness it contains. And this is not speculation. In 2026, research confirmed that the vacuum energy present inside cosmic voids, the fundamental quantum fields that pervade all of space even in the absence of particles, carries enough energy to drive this expansion. Even when you strip away ordinary matter, dark matter, neutrinos, cosmic rays, and radiation from the deepest interior of a void, what remains is not nothing. What remains is the vacuum of space-time. And that vacuum is not truly empty. It is filled with the quantum fields that underpin reality, and those fields carry a small but non-zero energy density. In the depleted interior of a cosmic void, this vacuum energy is the dominant component. It is the engine that drives the void's expansion, and through the cumulative action of billions of voids across the observable universe, the accelerating expansion of the cosmos as a whole. NASA's Nancy Grace Roman Space Telescope has been designed with this physics in mind. One of its primary science goals is to study cosmic voids as probes of dark energy. As Yovach Ni Vyazar of the Flatiron Institute and New York University explained in the research accompanying the mission, voids are regions dominated by dark energy, and their properties, their sizes, shapes, density profiles, and growth rates encode information about the nature of dark energy that cannot be extracted from any other kind of cosmic structure. The Roman telescope's wide field of view and deep sensitivity will allow it to identify and measure thousands of voids across a range of cosmic epochs, tracing how void properties have changed over time and comparing those changes to the predictions of different dark energy models. This observational program will not just refine our understanding of dark energy. It will test whether general relativity, Einstein's theory of gravity, holds true on the larger scales. Inside a void, the gravitational field is weak and the expansion rate is high. These are conditions where some proposed modifications to general relativity predict different behavior from the standard theory. If voids grow at a rate that does not match general relativity's predictions, it could signal the first observational evidence that gravity itself behaves differently at cosmic scales than the theory describes. But voids do not only shape the future of the universe and test the limits of fundamental physics. They also shape the galaxies that live inside them, and what they do to those galaxies reveals how profoundly the cosmic environment determines what kind of structure the universe builds. A galaxy forming inside a void leads a fundamentally different life from a galaxy forming in a dense cluster. In a cluster, galaxies are crowded. They interact frequently, stripping gas from each other through gravitational tides and ram pressure as they move through the hot intracluster medium. Star formation is often quenched, shut down by the removal of the cold gas that fuels it. Galaxies and clusters tend to be elliptical, red, and old, their star-forming days behind them. A galaxy growing alone on an open plane, far from the gravitational harassment of neighbors, follows a different path. In a void, galaxies tend to be spirals. They tend to be gas-rich, having retained the raw material for star formation, because no neighboring galaxy or cluster stripped it away. They form stars at rates that are different from their counterparts in dense environments, sometimes slower because the surrounding gas density is lower, sometimes extended over longer timescales because nothing interrupted the process. Void galaxies are not stunted or failed. They are alternative outcomes of the same physics operating under different conditions. The contrast is vivid when you look at specific examples. Consider a spiral galaxy sitting deep inside a large void, hundreds of millions of light years from the nearest cluster. That galaxy formed from gas that collapsed into a dark matter halo with relatively little competition from neighbors. No nearby massive cluster pulled on it gravitationally during its formative period. No dense intracluster medium compressed or stripped its outer gas layers. No tidal interactions with passing galaxies disrupted its disk. The galaxy evolved in what amounts to gravitational solitude. The result is a galaxy that, in many cases, retains its original gas supply to a remarkable degree. Void galaxies tend to have higher fractions of neutral hydrogen gas relative to their stellar mass than galaxies and clusters or dense filaments. That gas reservoir allows star formation to continue steadily over long timescales, producing galaxies that are bluer, younger in their stellar populations, and more actively forming stars at the present day than their counterparts in crowded environments. Their structures tend to be different as well. Void galaxies are more likely to be late-type spirals, with extended, well-defined disk structures and less prominent central bulges. In clusters, gravitational harassment, the cumulative effect of many small gravitational interactions with passing galaxies, tends to thicken disks, build bulges, and transform spirals into ellipticals over billions of years. Void galaxies are largely spared this process. They retain the thin, extended, rotationally supported disk morphology that is the natural outcome of gas cooling and settling into a spinning dark matter halo without significant external disruption. There is something almost paradoxical about this. The regions of the universe that contain the least matter produce some of the most structurally pristine galaxies. The Void galaxy did not have less opportunity to form. It had less interference, and the result is a galaxy that more closely resembles the idealized theoretical outcome of galaxy formation than the battered, transformed, environmentally processed galaxies that populate the densest parts of the cosmic web. The Void is not a hostile environment for galaxy formation. It is an undisturbed one. And undisturbed, it turns out, produces a different kind of galaxy than the one most astronomers are accustomed to studying. This makes Void galaxies valuable beyond their intrinsic interest. They serve as a control group. To understand what a galaxy looks like when it forms without significant environmental influence, you study Void galaxies. They are the closest thing the universe provides to a laboratory-controlled experiment in galaxy formation, isolated by hundreds of millions of light years of emptiness from the gravitational noise that dominates everywhere else. Studies of Void galaxies have shown that their properties carry information about the Void environment in ways that can be measured statistically. The luminosity function of Void galaxies, the distribution of their brightnesses, differs from the luminosity function in dense regions. Their color distribution is shifted toward bluer, more actively star-forming systems. Their morphologies favor disks over spheroids. Even their dark matter hollows, the invisible envelopes of dark matter that surround every galaxy, appear to have different concentration profiles in voids compared to filaments. This means that voids are not just empty space, they are distinct cosmic environments that produce distinct cosmic outcomes. The universe does not build the same kinds of galaxies everywhere. It builds different galaxies in different settings, and the most voluminous setting in the cosmos, the one that accounts for the majority of the universe's volume, is the Void. The galaxies that form there are the universe's majority population in terms of environment, even though they are a minority in terms of numbers. And the KBC Void, if confirmed at its proposed scale, adds a layer to this picture that is difficult to absorb. We may be living inside one of these distinct environments. The Milky Way, our local group, and the galaxies in our cosmic neighborhood may be Void galaxies, shaped by the underdensity surrounding us in ways that are so fundamental, we have never had an outside reference point to recognize them. The 2025 Baryon Acoustic Oscillation Analysis by B.H. Nick and Kalaidze Dis strengthen this possibility. If the KBC Void is real and has the depth suggested by the data, then everything we have measured about the local expansion rate, including the Hubble constant, has been measured from inside a void. Our local cosmic environment is not average. It is anomalous, and the anomaly is not a glitch or a statistical fluke. It is a structural feature of the cosmic web that has shaped the flow of matter around us, the apparent recession velocities of nearby galaxies, and possibly even the rate at which our own galaxy and its neighbors have formed stars over billions of years. This is the conceptual threshold that void science has crossed. Voids are not passive. They are not featureless. They are not static. They are active agents of cosmic evolution. They grow, driven by dark energy. They merge, creating larger supervoids. They shape the galaxies that form within them, producing outcomes different from those in dense environments. They distort the measurements made by observers inside them, bending the apparent properties of the universe away from the true global average. And they test the limits of fundamental physics, probing the behavior of gravity and dark energy in regimes that no other cosmic structure can access. The instruments deployed and planned to study them, Roman, Euclid, Rubin, and the spectroscopic surveys mapping galaxy redshift across billions of light years, are not studying voids as an afterthought. Voids have moved to the center of observational cosmology because they carry information that the dense structures cannot provide. And the picture they are assembling is one that inverts the intuitive hierarchy of cosmic importance. When most people think about the universe's grandest structures, they think of things. The largest galaxy clusters, containing thousands of galaxies bound together by gravity. The great filaments stretching hundreds of millions of light years, connecting clusters like bridges across the cosmic web. The superclusters, vast basins of gravitational flow like La Ni A Kai A, which encompasses 100,000 galaxies including our own. These are the structures that make the news. These are what fill the images. These are what the documentaries show when they want to convey the scale of the cosmos. But these structures occupy the minority of the universe's volume. They are the thin walls. They are the narrow filaments. They are the dense but compact nodes. The majority of the universe is void. And the biggest of those voids are not merely large empty spaces between the important structures. They are among the most powerful agents of change in the cosmos. They are where dark energy expresses itself most clearly. They are where the expansion of the universe is fastest. They are where the future is being written, not in fire and fusion, but in silence and distance and the slow, unstoppable growth of nothing. Every galaxy cluster you have ever seen in a photograph sits on the boundary of a void. Every filament is a wall between voids. Every supercluster is a meeting point where the edges of multiple voids converge. Remove the voids, and the cosmic web has no shape. The structures that seem so dominant, so defining, so fundamental are entirely dependent on the emptiness that surrounds them for their geometry, their arrangement, and their identity. The web is made not of matter alone, but of the relationship between matter and its absence, between the filaments and the voids they enclose. The biggest void we have ever found, the Eridanus Supervoid, with its 1.8 billion light-year span, its fingerprint on the cosmic microwave background, and its confirmed status as the most prominent underdensity in the dark energy survey's maps, is not a curiosity. It is a demonstration. A demonstration that absence at sufficient scale becomes architecture. That nothing, spread far enough, becomes one of the largest and most physically consequential features in the observable universe. And the final question, the one that void science has been building toward for 4 decades, and that no amount of data alone can fully answer, is what this means. Not for the measurements, not for the models, not for the next generation of telescopes. What it means for the picture of a reality that lives inside the mind of every person who has ever looked up at the night sky and assumed that the universe was defined by what it contains. That reckoning is where this ends. Let us be precise about what we are looking at. The Eridanus Supervoid is approximately 1.8 billion light-years across. That number has appeared several times in this story, and each time it has been surrounded by context, by the science of how it was found, by the methods used to confirm it, by the physics of what happens inside it. Now it is time to strip away the context and sit with the number itself, because the number is where the feeling lives. 1.8 billion light years. A light year is approximately 5.88 trillion miles. 1.8 billion of them produce a distance so large that the only honest response is to admit that no human being has ever truly visualized it. We can say the words, we can perform the arithmetic, but the intuitive faculty that lets you feel the difference between 10 feet and 100 feet, between a city block and a coastline, between the distance to the horizon and the distance to the next town, that faculty breaks down completely at cosmic scales. The number becomes a symbol rather than a sensation. So let us try to make it a sensation using the only tool available: comparison. The Milky Way galaxy, the structure that contains every star visible to the naked eye, every planet humanity has ever studied, every nebula and cluster and stellar remnant that constitutes our local cosmic environment, is approximately 100,000 light-years across. It is enormous by any standard that matters to a human life. Light departing from one edge when the earliest ancestors of modern humans were learning to walk upright would still not have reached the other side. The Eridanus Supervoid is 18,000 times wider than the Milky Way. The local group, the collection of galaxies gravitationally bound to our own, including the Andromeda Galaxy and several dozen smaller companions, spans roughly 10 million light-years. It is the neighborhood, the region of space where our galaxy has gravitational neighbors close enough to interact with over cosmic time. The Eridanus Supervoid is 180 times wider than the local group. The Laniakea supercluster, the immense basin of gravitational flow that was defined in 2014 and represents the largest coherent structure to which the Milky Way belongs, encompasses roughly 100,000 galaxies and spans approximately 500 million light-years. It includes the Virgo cluster, the Centaurus supercluster, the Great Attractor region, and the full extent of the gravitational watershed that shapes the motion of every galaxy in our extended cosmic neighborhood. Laniakea is one of the largest gravitationally coherent structures known. It is the address that contains our address. The Eridanus Supervoid is more than 3.5 times wider than Laniakea. You could place the entire Laniakea supercluster, all 100,000 of its galaxies, all its filaments and walls and clusters and flows, inside the Eridanus Supervoid, and it would occupy a fraction of the volume. You could fit multiple copies of Laniakea inside it, stacked in different orientations, and still have emptiness left over. The gravitational architecture that defines the motion of every galaxy we will ever visit, every star we will ever study with anything other than telescopes, is dwarfed by a region of space defined by the near-total absence of such architecture. This is not a rhetorical trick. It is a structural fact about the observable universe. The largest coherent thing our galaxy belongs to is smaller than the largest coherent nothing we have ever found. And the nature of that nothing matters. The Eridanus Supervoid is not a vacuum. It is not a sealed chamber emptied of contents. It contains matter. Galaxies exist inside it. Dark matter halos persist within its volume. Gas drift through its expanse. But the density deficit we described earlier, that 20 to 30% shortfall spread across a volume 1.8 billion light-years wide, represents a quantity of missing structure that exceeds anything a single number can convey. Consider what 20 to 30% less matter means at this scale. The cosmic average density includes contributions from ordinary matter, dark matter, and the radiation and neutrinos that thread through every region of space. A 20% deficit across 1.8 billion light years means that the mass which should be there, according to the average density of the universe, is simply absent, not compressed into some smaller region within the void, not hidden behind intervening structures, missing from the inventory entirely. The mass that is not there is not a small quantity. If you calculated the expected mass for a region of average cosmic density at this volume, and then subtracted the actual mass observed, the deficit would exceed the total mass of entire superclusters. Not galaxy clusters, superclusters. Collections of thousands of galaxies, bound together by gravity, representing some of the most massive structures in the cosmos. Their combined mass still insufficient to fill the gap between what should be inside the Eridanus Supervoid and what actually is. The void is a hole in the blueprint. Not a tear, not a defect, not a failure. A designed absence, carved by the same physics that built the filaments and clusters around it, but working in the opposite direction. Where gravity piled matter high, the void is where gravity pulled matter away. The blueprint of the cosmic web includes both the walls and the spaces between them, and the spaces are the larger component. This is the point where the science begins to press against something that is not purely scientific. It presses against the picture of the universe that most people carry unconsciously through their lives. The picture that shapes how they feel about their place in reality. That picture, for almost everyone, is dominated by things. Stars, galaxies, nebulae, clusters. The images from Hubble and Webb reinforce it constantly. Every press release, every documentary, every poster on a classroom wall shows a universe crowded with luminous objects, draped in glowing gas, punctuated by the brilliant deaths of massive stars. The emotional message of these images is abundance. The universe is full, it is rich, it is generous with matter and energy and light. That message is the minority report. The majority of the universe's volume is void. Not dark in the way that a room with the lights off is dark. Still full of furniture and walls and objects you would bump into. Dark in the way that the space between cities is dark when seen from orbit. The lights are far away. The structure is at the edges. The center is open and quiet and vast beyond any useful comparison to the things that surround it. When you see a photograph of the cosmic web from a simulation or a galaxy survey, the filaments glow. The clusters blaze. The eye is drawn to the brightest regions, the densest structures, the places where the most is happening. But if you shift your attention from the bright lines to the dark spaces between them, you see the real story. The dark spaces are larger. They are more voluminous. They are the dominant feature. The bright structures are the trim on a canvas that is mostly the color of nothing. This inversion from a universe defined by its contents to a universe defined by its absences is not a philosophical reframing imposed from outside the science. It is what the data show. The majority of the universe's volume, as we established earlier, belongs to the voids. The filaments, walls, clusters, and superclusters that contain essentially all the visible galaxies. All the star formation, all the light, all the chemistry that leads to planets and atmospheres, and, in at least one case, life, are confined to the minority of cosmic space. By volume, the universe is primarily void. Everything else is secondary. There is a deep human resistance to this idea. We are creatures of matter. Our bodies are matter. Every meaningful experience we have ever had has taken place within the thin, dense, luminous minority of the cosmos. We evolved on a planet orbiting a star inside a galaxy embedded in a filament of the cosmic web. surrounded by neighbors close enough to study and interact with. Our position in the cosmic web is not average. It is unusual. We are in one of the most structured, most populated, most gravitationally significant environments that the universe produces. We are the exception, living among exceptions, building our understanding of reality from the vantage point of the minority. And from that vantage point, the void is invisible, not because it cannot be measured, not because it does not affect us, but because the human mind is built to focus on presence rather than absence. We see what is there. We count what we can touch. We map the galaxies and call it a map of the universe. But a map that shows only the galaxies is a map that omits the majority of the territory. It is like mapping only the coastlines and calling it a map of the ocean. The Eridanus Supervoid is what happens when you fill in the rest of the map. And what you find is that the largest single feature on that map is not a supercluster, not a great wall of galaxies, not a filament stretching across 1 billion light years. It is a region where the map is almost blank. And the blankness is not passive. This is perhaps the most counterintuitive aspect of void science, and it is the one that carries the greatest emotional weight. The emptiness inside a void is not inert, it is dynamic. Dark energy operates there with less opposition than anywhere else in the universe. The expansion of space proceeds faster inside the void than outside. The void grows over time, pushing its boundaries outward, thinning the walls and filaments that surround it, merging with neighboring voids to produce ever larger regions of ever deeper emptiness. The absence is not static. It is active. It is expanding. It is winning. The cosmic web as it exists today is a temporary configuration. The filaments that connect galaxy clusters, the walls that separate void from void, the threads of matter along which galaxies formed and evolved, all of these are being slowly stretched and thinned by the expansion happening inside the voids. Given enough time, measured in hundreds of billions of years, the filaments will dissolve, the walls will fade, the clusters, bound by their own gravity, will persist as isolated islands, but the connections between them will be gone, severed by the relentless growth of the emptiness that was always the largest part of the picture. The universe's far future is a void, not a single void, but a condition of near-universal void, in which the remnants of the cosmic web float as disconnected points of light in an ocean of silence that dwarfs anything the present universe contains. That future is written in the physics that operates inside every void today. It is not speculative. It is a consequence of measured quantities, the density of matter, the equation of state of dark energy, and the expansion rate of space applied forward across time. And we are watching the process unfold. The next generation of instruments now surveying the cosmic web are not merely cataloguing structures. They are measuring the rate at which that web is being dismantled. Every void density profile those telescopes measure, every void growth rate they track across cosmic time, every comparison they draw between void properties at different epochs in the universe's history is a data point in the story of how the cosmos transitions from an interconnected web to a scattering of archipelagos, from connected structure to isolated remnants surrounded by the largest and most enduring feature the universe will ever produce: emptiness. The Eridanus Supervoid is the current champion of this process. 1.8 billion light-years of underdensity confirmed by gravitational lensing, traced in the cosmic microwave background, mapped in the distribution of galaxies and dark matter growing slowly and steadily as the universe expands. It is not the endpoint of the story. It is a snapshot of the story in progress. The voids will continue to grow. The supervoids will continue to merge. The structures that currently define the cosmic web will continue to thin. In the deep future, the Eridanus Supervoid will not be an anomaly. It will be the norm. Confronting this fact requires a different emotional register from the one that most space science encourages. The usual register is awe at abundance, the billions of galaxies, the trillions of stars, the unfathomable richness of the cosmos, piled high with matter and energy and complexity. That register is real and it is earned. The universe is astonishingly full of things, but it is more full of nothing. And the nothing is not merely the canvas on which the things are painted. It is the larger structure that gives the things their shape, their arrangement, their isolation, and their eventual fate. There is a particular kind of unease that comes from realizing that the most powerful forces in the universe are not explosive. They are not violent. They are not fast. The most powerful force in the cosmos is the quiet, slow, patient expansion of empty space, operating inside every void, pressing outward against every wall, thinning every filament, working across billions of years to reduce the elaborate architecture of the cosmic web to scattered points of matter floating in an ocean of darkness so vast that no signal from one island will ever reach another. This is not horror. Horror implies a threat, an adversary, a force that acts with intent. Dark energy has no intent. Voids have no purpose. The expansion of empty space is not directed at anything. It is simply the way the universe works, as impassive and impersonal as gravity, as fundamental and unavoidable as the speed of light. The unease it generates is not the unease of danger, but the unease of scale. The recognition that the universe operates on terms that are not merely indifferent to human concerns, but structurally dominated by a feature, emptiness, that the human mind is almost incapable of treating as important. We are built to pay attention to what is there. The predator in the grass, the fruit on the branch, the storm on the horizon. Every survival instinct, every perceptual system, every cognitive shortcut the human brain employs is tuned to detect presence. Absence registers only as the background against which presence appears. The void between the trees is not a thing. The silence between the sounds is not a thing. The space between the galaxies is not a thing, except it is. At cosmic scales, the space between the galaxies is the thing. It is the largest thing. It is the most volumetrically dominant thing. It is the thing that is growing while the galaxies remain fixed. It is the thing that will outlast every star, every cluster, every gravitationally bound structure in the cosmos. When the last star burns out and the last black hole evaporates, the void will still be there, still expanding, still dominating, still defining the geometry of a universe that has long since forgotten what light looked like. The biggest void we have ever found is terrifying, not because it threatens us. It does not. The Eridanus Supervoid is 2 billion light years away. It will never affect our planet, our star, or our galaxy in any way that a human being would notice. Its expansion will not reach us. Its gravitational influence on our local environment is negligible. In every practical sense, it is irrelevant to the daily experience of every person alive. But relevance is not the only metric that matters. The Eridanus Supervoid is important because of what it reveals, not about the void itself, but about the nature of the universe that produced it. We live in a cosmos where the most voluminous structures are defined by what is not there, where the largest features on the map are blank spaces between the features we were trained to look at, where the force that will ultimately determine the far future of everything is not the gravity that holds galaxies together, but the dark energy that fills the emptiness between them. The universe is organized by absence as much as by presence. Its architecture is built from what is missing as much as from what exists. The filaments and clusters and superclusters are real, and they are magnificent, and they contain everything that has ever mattered to any living thing. But they are the frame. The void is the canvas, and the canvas is larger than the frame will ever be. That is the structural truth that the biggest void forces you to confront. Not that the universe is empty. It is not empty. It is full of extraordinary things. But the extraordinary things are embedded in a larger emptiness that dwarfs them, shapes them, and will ultimately outlast them. The void does not negate the stars. It contextualizes them, and the context, when you finally see it clearly, changes the meaning of everything inside it. Every galaxy you have ever seen in a photograph is a bright point on the thin wall of a void. Every cluster is a node where void walls intersect. Every supercluster is a ridge between voids that are larger than the supercluster itself. The luminous universe, the one that appears in every image and fills every documentary and inspires every child who looks up at the stars, is the decoration on a structure whose primary material is nothing. This is not a bleak conclusion. It is a precise one. The universe does not owe us a structure that matches our instincts. It does not arrange itself to flatter the perceptual biases of a species that evolved on a small, warm, matter-rich world in a dense filament of the cosmic web. And what it is, when measured honestly and mapped completely, turns out to be mostly void. The Boötes Void, 330 million light-years of near emptiness discovered in 1981, was the first sign. The Eridanus Supervoid, 1.8 billion light-years of confirmed underdensity imprinted on the oldest light in the universe, is the current culmination. The KBC Void, the enormous underdensity that may surround our own galaxy and distort our measurements of cosmic expansion from the inside, is the possibility that makes it personal. And the physics of dark energy, operating preferentially inside every void and driving the slow unraveling of the cosmic web, is the mechanism that ensures the story is not finished. The voids are growing. The filaments are thinning. The architecture of the universe is being quietly restructured by the expansion of its own emptiness. And the biggest void we have ever found, far from being an anomaly or a curiosity, is the clearest window into what the universe actually is when you stop looking only at what shines. The universe is not defined solely by what it contains. It is defined equally by the scale and structure of what is missing. And when what is missing spans 1.8 billion light-years, when it leaves its signature on the afterglow of creation, when it dwarfs the largest gravitational structures to which our galaxy belongs, the word nothing stops meaning nothing. Emptiness, at this scale, is not a blank. It is not a gap. It is not the space between the important things. It is the architecture.